So my philosophy is that I got to tell you enough. I don't want you to be kind of flying in the dark about a lot of SEM, and I feel like some of the SEM texts and some of the things that you do, like the Klein text, is good on some things but bad on others. And we write books from our point of view and perspective. I want to give you enough of the background information so that you can understand how SEM works. You can ask questions about it later, and one of those things that's key to it is maximum likelihood. So if you come into this class and all you've taken up to this point is regression, that's cool. You're like most of us, regression, ANOVA, and so forth. But estimation in structural equation modeling, and actually estimation in everything else we do, is way different than what we do in the typical first-year sequence regression course. And that's a good thing. It's actually really good. We'll talk about why today's class. But without teaching a little bit about how we estimate things, particularly with maximum likelihood or robust maximum likelihood, I feel like you put a kind of a limit to what you can understand and what you can do. So what this lecture is about is not even specific to SEM. It's an SEM class. But you can take the knowledge from this class and go into, let's say, item response theory with it. It'll work there. You can take it over to multi-level models. It'll work there. You can take it to whatever class that comes next in your sequence, except for Bayesian. Although it still will work there, they just actually use different labels. It's pretty much the same thing, believe it or not. So everything that you do after this can use this method. So it's a little bit more broad. And actually, it speaks to a different point. So when I teach multivariate, I teach it every other year, spring semester. I focus on the likelihood-based techniques because I feel like those are the things that you see in print in journals more often than you see kind of classical. And these are slides that I would give in my multivariate class as well. So some of you who may take my multivariate next year, you may see this again. Get used to it. It's a bigger perspective than just for SEM. But that said, today is an introduction to maximum likelihood. Have any of you used maximum likelihood before? Yeah? No? Maybe? Who knows? Have you even thought about maximum likelihood before? Steve has. Yeah, that makes sense. You start getting around these things. What's that? Logistic regression. Yeah, absolutely. Anyway, we're going to talk about maximum likelihood. Where it ties into this class is last week we talked about distributions. Maximum likelihood takes those distributions, puts them together for all the people in your sample, and tries to figure out the statistics, the data, the results that you're looking for based on those distribution functions. That's it. It's insanely complicated. It can look really technical, particularly if you look at some really advanced text. Chapter 3 of Ender's book that I gave you today is a book about missing data, but I thought it did a really good job describing maximum likelihood for it. So I really like that book, so I hope that you read that chapter and had a chance to see it. It works in certain ways that are a little bit different. So I'm taking this perspective that if you're used to how things work, let's imagine, how many of you's favorite statistics package is SPSS? Yeah, rock on, right? So in SPSS, you click menu-driven SPSS? All right. So you know how you do like linear models, like general analysis, general linear model, or whatever the menus are these days. You put in your dependent variable, you put in your predictors, you click run, maybe, I don't know, something like that. And then in 2 seconds, up pops a box with all the results and it's done, right? The reason it works so quick is because it has what we call closed form equation. It has a literal equation that it takes your data, puts into the equation, and gives you results. Right? There's one-shot deal to it. For models just like that, that's fantastic. In fact, that's the best case scenario to have one-shot deal for it. But most of the models quickly outpace where you can have a one closed form equation to give you the results. So instead, maximum likelihood works with this iteration process, where it's kind of trial and error until it figures out what the best results should be. So that's a little bit different. But then we're going to keep going forward and saying, well, distributions are what underlies maximum likelihood. What about if our distributional assumptions are wrong? How do we fix it? How do we make it better? And that's what the next step happens to be, something called robust maximum likelihood. And robust, there's a jargon word for you. If I were to ask you before you even got to class, nothing about statistics, right? What does robust mean to you? Or what do you think of? What's the first thing, top of your mind, when you hear the word robust? What would be the word? Coffee, that's right. A really thick, hearty, like a dark, like maybe a stout beer with it. Anybody else? Any other thoughts? Hearty, thick. right? What's that? What?
Strength and endurance.
Strength and endurance. Yeah. I don't know that that really means the same here. Maybe something that can weather different types of data, maybe? Really what we talk about in terms of robustness, or robust in statistics, really doesn't have anything to do with copy. It means when you use a statistic or an estimator, and not all the things that you assumed are right, does it still give you just about the right answer? Case in point, in your basic statistics course, remember for measures of central tendency, you've got a distribution of data, and you would describe kind of where the average would be. You can use the mean or the median or the mode, right? If you're reporting skewed data, say annual income, right? You got this tail of people who are making lots of money, and then there's the bulk of us. I don't mean to be lumping myself with you. If you're in the lots of money group, awesome. Just pretend for right now. There's the bulk of us, toward not the tail, right? That tail tends to take the mean out with it, right? So if you have a bunch of people making, not a lot of money, and you got one billionaire, that billionaire is going to make the mean go closer to the billionaire and not look like anybody, right? Well, the mean is not a robust statistic for that reason, right? It doesn't work too well. Whereas the median, put that one billionaire in your sample, the median doesn't move, right? It may budge a little bit, but it's still 50 percentile above it, 50 percentile below it. Median is much more robust to outliers. What we're going to talk about is estimation when we're robust to distributions that aren't quite what we're assuming, right? And our assumption is multivariate normal for right now. So everything's multivariate normal. So things that aren't quite multivariate normal, like perhaps your Likert data. Likert data, it's your ratings on a scale, right? You ask a question, how happy are you today? And you have like strongly disagree, agree, whatever, the 5, 7 options. There are 7 different integers there. There's no continuous data. But if you assume them to be continuous, you might use a multivariate normal to describe it. Right? Multivariate normal would want those to follow a long continuum. So anyway, things like that. The other thing we're going to talk about at the end of the day is missing data. Don't you hate missing data? No. I must say this, don't you hate the subjects that just don't respond? Well, I'm one of those people. I am the worst subject. I know this is really bad. I guess I'm sort of a statistical anarchist, or like a data social science anarchist. Like if you give a study to me and you're using statistics that aren't robust, then my data is going to skew your result. So, I'll be the person filling out the survey in the extreme, like, there's nobody like that. Yeah, that's me. Anyway, missing data is kind of like that too. And believe it or not, maximum likelihood and missing data is a really good combination for the most part. So you get, in addition to so I guess the trade-off today, maximum likelihood can be really boring, although for me I love it, but I'm weird. Can be really technical, although I'm trying to streamline the technical part, trying to give you the big picture. But on the trade of it, it gives you a lot of good results, and it gives you a lot of good comfort or understanding what happens when you have missing data. Cool? Any questions before we jump in? So here's my questions for today's class. What's maximum likelihood? What is robust maximum likelihood? Why use either one of those? What additional hypothesis tests do ML or robust ML provide? And how are missing data handled in those? Now you'll note none of the above involves structural equation modeling, but this is kind of the fundamental beginning of SEM. Every structural equation model that we'll estimate in this class from this point forward will be using most likely robust maximum likelihood. So we have it always. It's always there. This is our intro to it. So we're going to use data from that chapter that you just saw. And if you remember the chapter, it said, imagine an employer is looking to hire employees for a job where IQ is important. And there are 2 variables. You have IQ scores and you have job performance. Right? But of course, in these data, the way that the book had described it, if you read the whole book, which is actually a really good book on missing data, they talk about maybe not all the data are complete, because perhaps you're working at a company where you have to have a minimum IQ to work there. I don't know what company that would be. Most likely not McDonald's. No. My first job was in a fast food joint. My IQ was pretty low back then. I don't know. That's where you wonder, state or trait, right? What's it now? Anyway, so that's where we're going to go. We're going to focus on mostly the complete data set where we've observed everything for the first part of class. At the end of class, we're going to talk about the other missing data sets that he puts in there, missing completely at random or missing at random. Those are two different words, almost like to me, even just before a few years ago, I'm like, yeah, that sounds about the same. Completely at random versus just at random. I guess it wasn't random enough. Like, what does that mean? So we'll talk about really what those mean, how it relates to ML, and how we go forward. Here's the data. We have IQ. We have the performance data over here. This is the first column. We have the performance data that Craig enters reports with the missing data that's missing completely at random. And then we have performance data that's missing at random. You notice, just jump foreshadowing here, and you can notice a trend here. Missing at random looks like the people who are at the lowest IQ don't have job performance. So you can think perhaps job performance was related to your IQ, because if you didn't have a high enough IQ, you wouldn't have a job. To have a job performance set. Whereas missing completely at random, we've got missingness all over right here. That missingness pattern is actually just kind of like you would say, let's flip a coin for everybody, or let's just give everybody a small probability that they will not have data at all. And that's it. So that is the difference between the two. Missing at random is there's something in the data that you've collected that could indicate why people are missing. In this case, yeah, if you knew their IQ, you know that they wouldn't have data. Whereas missing completely at random is, I have no clue. It happened all over the place. There's nothing in the data that I've collected that suggests it. But that's for later on. You have our descriptive statistics on the right. Mean IQ, 100, standard deviation, 14.13, and so forth. We're going to talk about the first two to begin with. Mean IQ is 100. Mean performance is 10.35. Those are numbers I just calculated. You know, you can calculate with a calculator. You use Excel. You can do whatever you like with it, right? We don't have to use some fancy estimator to do it, right? But this is what I like about maximum likelihood. Maximum likelihood will give it, we can go through the complicated process of ML, show you how you get to whatever you're working with, the distributional assumptions and everything else, and if it's working correctly, we should get the mean back. We should get the mean back for each. So that's why I want to put that there, is that all this complicated garbage that it's not garbage, it's actually why some of us have jobs. It pays the bills, right? This helps my children eat. But all of that is built because we have these assumptions that have to work through. It's not always as easy as finding a mean or finding a standard deviation. Now again, at the bottom here we have the covariance matrix. You remember the covariance matrix? Right? Covariance matrix is correlation's cousin. You any of you ever watched over the holidays Charlie Brown? Like they had a Charlie Brown special on one of the channels. My daughter was with me over the holidays. So I sat there. It's pretty cool. So she just turned 8 over the holidays. So you have an 8-year-old watching Charlie Brown. Something I probably watched when I was younger. You know Snoopy. I don't know if you know. Snoopy has a cousin. You know Snoopy's cousin? All right, I'm going on an anecdote here. His cousin's name is Spike. And this is what he looks like. Right there. He lives in the desert. And he's kind of got this little thin, ugly mustache. Now, you never hear about Spike, right? And that's what that's covariance to correlation, right? Covariance is the spike of correlation, right? It's the cousin who shows up. He just kind of grifts along. The thing we were watching, he needed the place to crash for a while before he went back to the desert. Like, yeah, that sounds totally right. This is sorry, I don't know where this came out. Evidently, if it's boring for you, look, imagine teaching it. No, just kidding. No, this is it. This is covariance for you. All right. So covariance matrix, just to remember, I keep dwelling on this because remember, in multivariate normal that we talked about last week, the covariance matrix is one of its terms. It's not the correlation matrix, it's the covariance matrix. So everything that we do is expressed in covariance. So here, the diagonal of this is the variance of each variable, which is the standard deviation squared. Right? The off diagonal is the covariance, which is like the correlation, right? It's positive, which means that there would be a positive correlation, but it's in the scale of the units of each of the other variables multiplied. So covariance at 19.5, I don't actually know what that means. The first thing I would do if I wanted to interpret that, I would say, hey, let's change it into a correlation. And you could do that by dividing it by the product of the standard deviation. So take 19.5, divide it by 14.13 times 2.68. Those standard deviations are like the units. It cancels the units of both of those, and now you have a correlation for it. So, cool? Always got to go back to Snoopy and not Spike. Anyway, I like that picture though. You know him? Have you seen him before this class? This isn't. Oh no. All right, that's fine. I might inspire you to go watch some. I don't know. All right, so we're going to work with that, and if we do everything correct, what we should find is that we find these answers in our multivariate normal using maximum likelihood. Those are the numbers we're going to come to, the data. We could calculate them by hand if we wanted to using the methods of the formulas that we've seen before, but our algorithm will actually estimate them, but it'll estimate a lot more too. Okay, so why is estimation important? Have you ever talked about estimation in your classes before? I see blank stares. Everybody's looking around. Who did it? Who talked? Who's talking? I know some of you have been in classes that have. Some of you REM students, my program, I know Billy's class, you talk, Dr. Skorupski's class, you talk about it. I'm sure other classes may do it, but it's really technical stuff, right? But it's critically important. You think about it, we question everything in science, right? We question whether or not the controls were in place in your study, who the sample was, whether or not they were paying attention. But then you go and plug your data into some program, it runs behind the scenes, and it comes back and tells you numbers, and everybody's cool about it, right? Like if you were to ask me, hey, Templin, this is an absurd example, right? You're like, I can't figure out what the mean IQ should be. What is it? You can use the Templin estimator. It's called a cell phone, right? You call me. I answer the phone. You're like, what's the mean IQ? I will give you an estimate. All right? It's 20. Write it down. All right? So then you go and write it up, and for whatever reason you're publishing or you're doing your master's, but your dissertation defense, and you show your committee, IQ mean is 20. Do you think they're cool with that? Why would they not be cool with that? Why 20? Who gave you that number, right? When I was in grad school, I had a friend, Bob. We used to work in a off campus and it used to be an old moose lodge. It was like, evidently there's an order of old men who like to get together and call themselves moose. And they had a lodge, like an Elks Lodge or something like that. And they no longer used it, but somehow we ended up working out there as grad students. Anyway, and we were working on problems to try to get big problems to estimate, and we could never do it. So I was like, well, I'm going to go call your dad and see what he would tell me. It was Bob's dad estimator. All right, so you call me and you get a 20, and you call Bob's dad, and he gives you, well, I think that's a 7. All right? What do you think? You trust Bob's dad? You trust me? All right? What can you say, like, in the long run, if you kept doing repeated samples of your study, you call me and ask for the Templin estimator, and I just keep telling you 20. All right? You change the variable out. Oh, it's 20. Would that work? Right? What I'm trying to say is this. Why do you trust SPSS? Or why do you trust SAS? Or Excel? Oh no. I'm shaking that trust, right? Should you trust them?
There's like math.
There's math! Somebody did math once. What math?
Well, for what program?
Oh, just saying, huh? Is there math behind my result?
No.
No. What if I could say to you, there was a way I could get a result and tell you that not only that you should trust 20, but in the long run, 20 is going to be the best result. In fact, we could even use 20. We could put 20. We can give it a distribution. We can say how much error there is based on your data. Would that be better? No. We could use math to figure that out. So anyway, the point is, if you ask me, I'm like the black box that didn't use math. But we can use math and develop estimators for data to give us numbers that we can believe in. And once again, what am I talking about in terms of numbers? I'm talking about, like, think about it in regression, your regression beta weights, right? Your sigma squared error. In your homework, in Levon, you know how they, at the bottom of the output, you had like the numbers, the beta weights you had to interpret, and the variance? Those numbers came from something. Why would you trust them? Anyway, here's how estimation works, more or less, which means I'm fudging a little bit here. We would like to, estimation routines work in generally one of these three ways. We use them to minimize something. Right? So minimize, it's a mathematical term, but you may have seen this in regression. You hear in regression the words least squares. Have you heard that before? Least squares means in regression you're trying to find the beta weights so that when you plug them into a regression line and you make a predicted value, that the squared difference between the predicted value and the data was the smallest, the least squared difference, right? As a minimization process. And typically you see these estimators have forms like least squares. Least is in the title somewhere. And some of them even add more adjectives. I believe these are adjectives to it, like generalized least squares, ordinary least squares. That sounds really lame, though. Did you use ordinary least squares? Those people in econometrics love that. Ordinary least squares, weighted least squares, diagonally weighted least squares, WLSMV, which is M+'s version of diagonally weighted, iteratively reweighted least squares, and on and on and on. There's a lot of things to it, but generally speaking, it's something to go with, I'm going to guess about my model parameters, I'm going to plug them into my model, I'm going to see how far the square difference is from some type of term, either in my model or my data. Right? The thought being, if I can make that difference as small as possible, I get the best estimates possible. And that sounds pretty plausible, right? If you would have called me and said Templin was the mean IQ, and I said, well, I used the least squares estimate, and I got 20, at least you'd be able to say, well, that's the number that came about that got close enough to the data for it. Right? So that's where you usually start in statistics. But quickly, not everything, least squares do show up, you see that, but typically we'll find that that's the estimator of last resort. We use that because some of the other better estimators, and why they're better I'll tell you in just a moment, why they're better, may not work, or may work, but you may not have enough time for them to work. So for instance, if you take a 15 factor analysis, but your data isn't multivariate normal, maybe it's categories, right? It may take you 2 weeks to find the result. Have you ever pushed a button on a computer and waited 2 weeks? Seen it working? You think it's working, it's not telling you anything. What's the longest you've ever waited for a result to come back from a stat package? Seconds? 5 hours. Oh, that's good. It's getting there. But yeah, if you have to wait so long that you can't use the result, and better yet, you know how it works. You don't just run one model. There's always run it and it didn't work. So you got to change something, run it again. That process will drag out forever. So that's why we use least squares most often. It's a last resort type thing. A better thing, or what else comes up after that, is something called maximize something, or we maximize a function. And generally this is where maximum likelihood show up, right? We have these, if we make some assumptions about our data, like the distribution of the data or the error term, implicitly or explicitly, we can use that distribution to form what's called a likelihood function. Once we find the likelihood function, we can plug in the parameters or the statistics, the beta weights, that give us the peak, the maximum. That's maximum likelihood. We may, other terms that you'll see up here, have a residual maximum likelihood, which is maximum likelihood on residuals. Again, residual is a terrible name. This is used a lot in multi-level models. We could use it in SEM, we usually don't. Robust ML, you'll see that today. These are typically the gold standard estimators, and they're the gold standard because by statistics, we can show that if you use these estimators on any type of model, so long as you have a big enough sample size, some really good properties hold. Right? So instead of having to say, well, Templin told me that was it, right? You could say, oh, I know that this is the number because I'm guaranteed it to be that way if I get a big enough sample. It's the right number. It is the unbiased, consistent value that it should be. Right? It also, we'll see those properties as we come up today, but that's maximum likelihood. People like them the best. Then the last part of it is a little bit newer to statistics, certainly. We use simulation to sample from something. This is Bayesian Markov chain Monte Carlo is what it's called usually. We won't see that a whole lot in this class, if at all, but that does happen a lot more in very complex problems. The reason why we don't see that in this class is even though we have to use maximum likelihood, so we have this iterative algorithm that doesn't just have a closed equation. The closed equation is a lot easier to work with when you're assuming things are multivariate normal. And most of the things we assume in this class are going to be multivariate normal. If you switch that from multivariate normal over to something that's like you have categorical data and you use a categorical distribution, something like a Bernoulli or binomial or one of these other words, then maximum likelihood will take a lot more time. You can do it, it just may take you longer than we have time in the class to do things. So that's where you might see these other methods. These methods on the bottom actually have better properties, similar properties to the maximum likelihood methods as well. How are we doing? Cool. So what is the awesomeness about maximum likelihood? 3 things. This word asymptotic, there's another buzzword. What that means is as n goes to infinity, right? As your sample size goes up to infinite proportions, infinite numbers, proportions, numbers, big things, these things happen. Right? Remember the central limit theorem? Right? It's essentially that. Right? As your n goes to infinity, or as your repeated experiments go on and on and on, you get this normal distribution of your mean, and we use that for things. Here, we get these following properties. We get consistent estimates, which means the estimate converges to its true value. Right? What it should be. That's cool, right? That's really good. That means whatever it should be, and you don't know what it is, but whatever it should be in truth, it will converge to it should you get enough sample, right? That's what you want to know. Why did you use ML? Because it gave me the right result. That's why. Right? That's generally why we think of it. The next one is a little bit nicer when we start to do statistics. We end up finding that our estimates follow a normal distribution. What does that mean? If we wanted to tell whether or not, if we had a regression line with beta 0 plus beta 1x, and let's imagine x was a 0 or a 1, right? Then the test of whether these two groups, this is a group, beta 0 is the group mean for people who are 0, beta 1 is the difference. The test of that would come from whether beta 1, if we want to test the mean difference, it's testing whether beta 1 is equal to 0. Like we call that a null hypothesis, right? Right? Well, if we go estimate this with maximum likelihood, we might see the following. This is where the estimate of beta 1 is. Sometimes we put a hat over it to say that's estimated. We get a standard error of the estimate from maximum likelihood directly. And putting those two together, we get all we need to know that this is a normal distribution. So if we know it's a normal distribution, if here's where 0 is, we can form kind of a p-value, right? We can see how likely 0 happens to be according to this, or 0, or how likely or more extreme this result is in the normal distribution. So we can use that to give us hypothesis tests. That's all from like theory of maximum likelihood. As your numbers get big, your estimates follow a normal distribution, and we use normal distributions to figure out whether these things are significant. That's cool, right? I'm sorry. I think that's cool. Let me tell you, that's cool. Right, that's cool. Yeah, that's what I'm looking for. Anyway, last thing, efficiency. That standard error that we talked about. Every type of estimator will have a standard error. They'll give you an estimate of how much error there is, it's usually sampling error related in your data. If you use ML, you'll find that you have a smaller standard error than any other estimator that you have. So those are 3 things that make ML the best estimators. Why people refer to them as kind of the gold standard for what we do in statistics. So you might be thinking to yourself, why didn't I learn this in regression class? Right? Sure enough, in regression, if you have that regression line like this one right here, its least squares estimates and its ML estimates are identical. Right? How about that? You were using ML the whole time. It just happened to be you had a result that you could find with an equation. So anyway, the rest of what we're going to do is with ML. So how are we doing? Questions? Complications? Comments? You remember this formula? It's normal because 2 pi. 2 pi shows up. That's how you know it's normal. Anyway, we have to assume a distribution about the data or about something in our analysis. So what we're going to start off with is just a single variable, and we're going to assume that it follows a normal distribution. And this, remember from last week, this function right here, we plug in numbers, right? We plug in the data, we plug in the mean, we plug in the variance, and what do we get? We get the height, right? So each of these heights, here's a mean, here's a variance. That tells us essentially what happens to the shape of the distribution is. So if you have any given value of x, say x equals 1, its height is, its height is like right here on the line. Right? So something like that. That's all the distribution's doing. And here we have 2 examples. Imagine with our IQ variable that we knew that the mean of IQ was 100 and the variance was 189.6. Right? We don't know that. Those are our sample estimates, but let's just pretend. We have to pretend something to make this work. We plug those 2 numbers in, and we can say, what's the relative likelihood of someone with a 100 for an IQ versus someone with an 80? Right? We plug in the value for 100, we get a height of 0.021. Plug in the value for 80, we get a height of 0.0101. So those numbers, remember we said, that by themselves they don't really do a whole lot for us. We just tell us which one's more relatively likely to occur. And this is telling us that it's much more likely that we observed a value of 100 from our sample than we observed a value of 80 from our sample. Those aren't probabilities, though. They're just weird heights and likelihoods. One thing I wanted to point out to you about that is in R, to find that, there's a function. And if you go to the slide, the web page for this class this week, elementary school teachers. Sorry, I'm loud and they hear me, so this happens. If you go to the graphs and distributions page, this one, I'm going to go to the analysis page. This is the HTML file. This is what the R file gives you when it works. But there is a function where if you want to plug in your mu, your sigma squared, and your x and get the height, the function you want to use is this one right here, dnorm. I don't know if you can see that. Dnorm, right there. Right? You give it x, you give it mu, you give it square root of sigma, and I plugged in mu was 100, sigma is 189.6. I actually defined a range of x's. You're not going to have to do that for your homework, but for your homework, you're going to have to do a single value of x or multiple single values of x. So this is kind of the answer to some of your homework right here. Dnorm. It gives you the height. Sorry. Foreshadowing homework. Let me just say it real quick. This week's homework, this next one, has the potential to be a little bit esoteric and difficult. But it involves dnorm, which is a univariate normal height. And it will involve a different version of dnorm, the multivariate norm. I believe it's MV dnorm later on. And you'll see that in my slides here. What I'm trying to get you to do with homework and what my motivation for it is I feel like trying to provide some type of mental representation of a likelihood, of a height, of data, of whatever, what the computer is doing. Because I think that will help you understand the process by which we come about getting our estimates. but that's it. And besides, there's 2 weeks to do it, so don't panic. But you'll learn everything you need to know to do it, most likely today. So, but okay, going back to the lecture. Maximum likelihood estimation begins by building a likelihood function. I actually asked question number 2. The starting point. Actually, no. Question 3. The sample likelihood function is formed by. I believe Ender's chapter started like a heading that was not too far in it that said the starting point is. Hey, that's in my slides. I don't believe I followed his chapter when I built the slides, but we're thinking the same thing at least. It's nice. The likelihood function is no different than that distribution function that we just had a couple slides ago. That's a likelihood function in some respects. However, it's a likelihood just for one person. And what we have when we collect a sample of data is a likelihood that comes from the entire sample all at once. Right? Each person is kind of contributing to that. So our likelihoods are each person's likelihood function put together for the sample itself. That sample is like saying, what's the likelihood this occurred in all of my sample observations all at once? Right? A joint distribution. Very much like a multivariate normal is a joint distribution. So let's consider this for one observation. Here's a one observation likelihood function. To think of this is not the sample yet. This is just one person, right? But this is how the process works once we go from one person to the sample. Let's assume that we have observed the IQ for this person. And furthermore, we know this person's IQ is 112. All right? And we assume that it comes from a normal distribution, and we have a variance of 189.6. We're just making the variance known just to make it so that we can find a height to it, right? The question you want to know, okay, I know the variance, and I know this person's IQ is 112. What's the mean of the distribution this person came from? What's the most likely mean value? It's where you have this likelihood function, right? We know x. We know sigma squared. The only thing we don't know is mu. So if we plug in values of mu, we get different values of heights for all the different mu's there are. And sure enough, wouldn't you know it, the one with the biggest value of the height will happen to be the maximum likelihood estimate for mu? That's it. Right? It sounds kind of ridiculous, and in fact, when we plug it in for one person, we plug in those values, and we can figure out what that happens to be. So I did this in R, and you can find my code online for how to do this. You don't have to do this in R. I'm not asking you to plot these things. I just want you to figure out the height. I just literally tried out values of mu. And I used dnorm to give me the height of all of it. And sure enough, the likelihood happens to be 0.029, or the value that the likelihood, the peak, gave me a value of 0.029. That was the highest value of likelihood, and it happened to occur at a value of 112, which is the data. And that's that one thing. Because we've only observed one person, right? And because we're assuming this normal distribution, remember the mean is the most likely thing to happen in the normal distribution. So with one person, the most likely distribution it came from has a mean that's equal to the value of the data they gave us. Right? But if we had more than one person, then that's going to change, right? We may have 112 and 114. And that's the process, right? We sort of guess what the values happen to be. Right? We guess values for the thing we're interested in estimating, the parameter. And then after that we go from there. Battery issues with my pen again. Questions? There we go. Well, you have one. That's right. Alan's got a surface. Like it. Okay. So if we go from one observation, we can go up to the sample, and this is where the math gets really terrible. But you can think of it this way. In our sample, we assume people to be independent most likely. And it's a very convenient thing that people are independent, because in statistics, when you have distributions that are independent, the joint distribution is formed by taking their product. This is very similar to the idea that if I had a coin in my pocket, a fair, let's say a quarter, I flip it. What's the probability it lands heads up? 0.5. Okay, got that. What's the probability I flip a second time and get the heads? Another 0.5. So you'd say, well, what was the probability that I observed 2 heads off of 2 flips? It's the multiple of both of those, 0.5 times 0.5. The multiplication that you're doing there is implied because you're assuming that each coin flip is independent of each other. Right? And that 0.5 is that flip's distribution function. Right? It's a discrete term, so it's actually a mass, but it works the same as these little distributions with curves and everything too. So if we have a sample of people, what we do is take the distribution for each person, right here, this is the normals, and multiply them together. Right? Person 1's normal PDF times person 2's normal PDF times person's all the way down. Right? And what this ends up being in terms of statistics, this big pi there actually is not 3.14, which is little pi. Right? That is the product symbol, which says multiply whatever's after this many times. Right? So this says multiply from person 1 up to person, oh, I don't want that. Person 1 up to person n, right here, this function together. And I rearrange terms. If you do that, because we're working with with exponents and products, remember exponents, when you take a product of exponents, it changes the exponent itself. It's like summing them together. And so that's what you end up getting, this ugly looking form. I'd say that's a high degree of difficulty thing. But again, it's normal because it's 2 pi in it. So. Okay, we're almost to break. So this ugly term, this big ugly function right here that happens from all of our data is what we can use to figure out our sample mean and sample variance if we wanted to, right? Because from each person, we have the data. We have all the x's. But if we assume the mean to be the same for each person and the variance to be the same for each person, which is what we do when we take a mean or we take a variance, then all we need to figure out is what mu and sigma squared happen to be that give us the biggest value from this function. Right? That's it. That's maximum likelihood. Figure out mu, take a guess. Guess a mu, guess a sigma squared, plug them in. Right? And there's only 2 of them, only 2 numbers. We don't know mu, we don't know sigma squared. We could plot it, and I will plot it when we come back from break. Do you have any questions? I feel like I'm starting to talk at you a little bit. Are you getting this? Okay, that's good. I just wanted to make sure that, because sometimes I can just keep talking and everybody's like, I don't get it. And I'm so far gone that you don't want to reel me in. Reel me in, please. Let's take a break for 10 minutes. All right, thank you.